This is our presentation on the demographic effects on gun ownership in New York City. So gun violence is a dangerous and alarming issue that has been growing exponentially over the past couple of years across the United States and especially in New York City. This, of course, has entailed growing concerns regarding gun accessibility in NYC and the US overall. We explored gun ownership in New York City to gain a clearer understanding of how different demographic indicators impact whether or not someone chooses to own firearms. We chose to specifically study New York City because of the high concentration of gun-related violence in that region. We focused on two different data sources for this project. The first one being the Citizens Committee for Children of New York, and the second one being the New York Police Department.
Our steps for this project were data preparation, exploratory data analysis, using Lasso Regression to create a linear model, and finally we ran a decision tree and random forest model. To prepare and clean the data, first we loaded in two data sets. One contained data on the number of handgun permits in New York City by zip code, and the other contained demographics of the 59 community districts in New York. We calculated the number of handgun permits per 100,000 people in each community district. For the second data set, which included the 30 demographic factors, we filtered the data so only the most recent data from 2019 was used. After that, we merged the two data sets together. Finally, a column was added in the final data set, sorting the communities into the 5 boroughs in New York City. After we cleaned the data, we performed EDA to create various graphic representations of the data to understand it better. First, we created a bubble map of the 59 community districts for the number of handgun permits per 100,000 people. Some areas with significant number of handgun permits are Totenville and Staten Island, which is known for being a suburban residential area and extremely family-oriented, and Throgs Neck, which also has a high number of permits. It is mostly working and middle-class neighborhood, and it is also very family-friendly. Next, we created a bar graph of the 10 community districts with the highest number of handgun permits. Some interesting things to note are that the community districts with the highest concentration of handgun permits are in Staten Island and the Bronx, which have a relatively low population density. Surprisingly, the most populated borough, Manhattan, does not appear on this top 10 list. Next, we take a look into one of the demographic factors. We made a bar graph with the 10 districts with the highest percentage of homeowners. Both the Bronx and Manhattan did not make it into the top 10, which could be because of the higher price of buying properties there. Furthermore, because Manhattan is so densely populated, more of the properties there are rented to facilitate a higher population density. On the other hand, Queens and Staten Island appear to have many more homeowners. Finally, we created a scatter plot of the handgun permits per 100,000 people versus the number of reported violent felonies for each community district. Surprisingly, there was not much apparent correlation between these two variables, implying that community districts where people own guns are not actually more violent. However, this only includes gun owners with legal gun permits, so this graph could be implying that districts with more legally obtained firearms are safer.
The first technique that we used to analyze our data was lasso regression, which consisted of 3 steps. First, we used the lasso function to select the most significant variables in our data. Next, we created a linear regression model using the variables that were selected by lasso. Finally, we used the ANOVA function to generate a significance value for each variable and performed backward selection to eliminate insignificant variables. The first function that we used in this process was lasso, which stands for least absolute shrinkage and selection operator. Lasso is a regression technique for multiple variables. It essentially creates a linear regression model and tries to minimize the weights involved. That is, it tries to make as many weights 0 as possible. Now, if the weight or coefficient of a variable is 0, that essentially means that it's entirely insignificant to the final model and can thus be removed. Lasso therefore removes all of the variables that have weight 0 and returns the remaining variables in a data set. For our process, the remaining variables were the percent of people who own their own homes, the population of the borough, the number of resident jobs in healthcare, the number of resident jobs in hospitality, the number of resident jobs in management, and the number of residential jobs in administration. Next, we use the ANOVA function, or analysis of variance. The ANOVA function takes in a linear regression model and returns a significance value for each variable. We then removed any variables whose significance did not pass a certain threshold, which left us with 3 of the most significant variables out of our predictors. The 3 variables that we were left with after this process were homeownership, or residents of occupied housing units who owned their own unit, resident jobs in public administration, and resident jobs in management and professional services. Our final linear regression model is shown by this equation, which assigns a linear weight to each of the 3 variables that we were left with.
So the second technique we used to analyze our data was random forest. Starting from decision trees. A decision tree uses recursive binary splitting to split the predictor space to minimize the residual sum of squares in the resulting spaces. In our case, our data with 30 predictor variables are split into different spaces. Every observation that falls into one predictor space will have the same prediction. The graphic on the left is the result of our single tree. Despite results from this tree, we used random forest to get the most important factors because it has a higher level of accuracy. So instead of using the entire data set, random forest uses samples to create multiple trees. At each split, the algorithm is limited to only consider a majority of the available predictors, because if there's one very strong predictor, then in the collection of trees, most will use this strong predictor as its top split, thus creating similar looking trees with high variance. Random forest gives the non-strong predictors a chance, making resulting trees less variable. In our random forest, we randomly selected 10 variables to be selected at each split. The results of our random forest are shown in the right graph. Ink node purity measures the total decrease in node impurities from splitting on the variable. The higher this value is, the more effect the predictor has on node impurities, thus the more important the predictor is. So our random forest plot showed that the most important variables in predicting the number of gun permits are homeownership, the jobs in administration, and jobs in hospitality. So here is a comparison of the results from both Lasso and random forest. They both indicate that home ownership and resident jobs in public administration are very good predictors of the number of handgun permits. This makes sense because most places for rent may have restrictions on guns, and jobs in administration may need a gun for either self-defense or because it's job required. However, you can see the difference between them is that Lasso had jobs in management and professional services, and Random Forest had jobs in hospitality and restaurants.
It's important to recognize that our project may have biases. For instance, gun ownership is not accurately reflected by gun permits. For example, illegally owned guns. Some demographics might be more likely to legally own guns. For instance, homeowners might be more likely to legally own guns, or they may have more access to handgun permits. In addition, our study only focuses on handguns, so there might be a distinction between handguns and other types of guns, as other types of firearms may be affected more by other demographic factors. So, expanding this beyond our own research, we can have a study that is across all of America, as we can't just assume that New York City's handgun permit data is an accurate reflection of the entire country's data. And having this broader data would provide valuable insight for advocates on who their target group is. So because we can't just assume that our notable variables are an accurate reflection of the whole country, having this additional data would be crucial to understanding what demographic indicators are most useful for addressing issues like gun violence. And this data could be potentially helpful to government officials, policymakers, and police departments across the country. Thank you for listening to our presentation.
Hi everyone, my name is Sidarth. Today I will talk about my project, multi-modal movie genre classification. This is a brief agenda of the presentation. I'll first talk about why I chose this particular problem and other motivation. Then I will explain the experiment that I designed and the result that I obtained with different models. I was very excited to work on this topic for a different reason. First, I wanted to explore computer vision and MLP techniques and multimodal PERTs. I further wanted to utilize BERT and other state-of-the-art models that have been very popular recently. I'm excited about using what I have learned to solve real-world application. I specifically want to classify movie genres using movie description and poster, since this is challenging and there hasn't been many studies or attempts to tackle this problem. A movie usually has more than one genre. For example, Harry Potter series are tagged as adventure, fantasy, children literature, and so on. As a result, predicting genre is a multi-label classification problem. It is worth noticing that there is a difference between multi-class and multi-label. In multi-class problem, classes are mutually exclusive. For multi-label problems, each label represents a different classification task, but the tasks are related. To classify movie genres, different deep learning models were compared. First, I built Unimodal models, that meaning that I use only text or only use image. After that, I concatenated models, as we can see from the picture above, to make multimodal models in order to understand the importance of aligning visual and text signals in the movie genre classification. I got the IMDb movie dataset from Kaggle. The dataset includes movie information such as movie plot, description, ratings, review, and dates, and so on. Then I scrapped movie poster given the movie information from the dataset. I use movie description and movie poster as our input features and genre as our class label output. From the original dataset, we remove movies that do not have movie description. After plotting the frequency of each genres in the dataset, some genres were dropped because each of their contribution is less than 3% of the class label. As a result, there are 10 genres are used as our class label. The final dataset has 10 class label output for each movie. This is an example of class label outputs for each movie. We can see from the picture above here that Home Alone is a comedy family drama movie. After applying one hot encoding, it becomes a multi-one hot encoded vector. Now I'll talk about the baseline model. Starting from the simple baseline model, I use majority vote. From the EDA step before, I observed that majority class is drama, so I labeled all movies with only one class, which is drama. The baseline model achieved 0.24 Hamming score. Hamming score represents the number of labels we make correct prediction out of union of all the predicted label and all true label. We can think of it as accuracy here. I will talk about unimodal models. For LCM model, movie description text sequence put into an embedding layer, which is the pre-trained word-to-vec embedding. 2 layers of LSTM were stacked and put into a fully connected layer with sigmoid activation. For BERT model, BERT based on case model was fine-tuned on movie description, and we took the first output of the final layer of the BERT model, which fed into a classifier with sigmoid activation. LCM had a value of 0.44 and BERT had 0.54. BERT had a better performance to classify movie genres based on movie description. For CNN model, movie posters were input of the CNN structure, which consists of 2D convolution and max pooling layers. The last max pooling layer output was flattened and put into a fully connected layer with sigmoid activation. A standard ResNet 50 was fine-tuned on movie poster with the average pooling as output. Each movie poster has 2048 dimension vector, and the vector was put into a fully connected layer with sigmoid activation. CNN had a value of 0.39, and ResNet 50 had 0.32 in terms of Hamming score. CNN had a better performance to classify movie genres based on movie poster. One-off factor can be due to overfitting issues. ResNet 50 learned the training set very well, but it was not able to generalize on the test set. This might be caused by too large network capacity, too many degree of freedom in parameters. Also, movie poster might not include deep semantic meaning to classify movie genres from seeing the model performance for both of the models. Now I'll talk about multi-models. For a stack LSTM and a CNN, the text sequence for input to an embedding layer. I use Google's pre-trained word-to-back embedding. The embedding layer is followed by two stack LSTMs whose outputs were put into a fully connected layer. The images are the input to a CNN. The output of the last max pooling layer is flattened and fed into a fully connected layer. The fully connected layers of the LSTM and CNN then concatenated and fed into till the final fully connected layer. The last layer has an output size of 10, each correlating to one genre. For BERT embedding, we use the pooling layer at the end of the BERT model to take an average of token embeddings. For image embedding, we use a max pooling layer to get a 2048 dimension image embedding and flatten it. We concatenated the image embedding and the BERT embedding into fully connected layer with sigmoid activation. Among all the models, BERT had the best performance out of models, which outperformed roughly 130% compared to the simple base model. We can see from the table above that the BERT model did best predicting drama, comedy, action, horror, and thriller genres in terms of FN score. The dataset has more movies with those tags, which explains why the model did well. On the other hand, movies with family mystery genres pose a challenge to our model. One reason is the lack of those models in the dataset. Another reason is that the model finds it hard to differentiate between mystery and crime text. We have learned a lot from the project and come up with several key takeaways. First, text-only unimodels, such as LCM and BERT, perform better than the image-only unimodels, such as CNN ResNet 50, which indicates that the movie description has more signals to classify movie genres and movie posters. Also, comparing the model performance between unimodal and multimodal, stack CNN and LSTM had a slightly better result than only CNN or only LSTM. On the other hand, BERT and ResNet 50 did not perform better than single BERT. One possible explanation might be substantial parameter to train model. Since ResNet 50 and BERT each has many parameters to tune, it took high computational power to fine-tune the model, and better hyperparameter tuning was required. It was also worth mentioning that scores that we achieved seemed to be high, but it was limited to two genre imbalance issues. But lastly, predicting genre is a challenging task, even for a human being. That's all for my presentation, and thank you for listening.